Today, we start a new part C of Module 1, Power of Algorithms and Data Structures. All right, C.1, Horner's Rule. Remember, our goal, we want to find an efficient algorithm to do the polynomial evaluation. So let's continue our problem solving. Yeah. So we did part of it. So now let's continue to get a complete solution. Yeah. All right, so right now we just did a simple example. Yeah, so let's recall a little bit. We just solved this special case where n equals to a quadratic polynomial. And after the factorization, so look at here, after we did factorization, we changed the structure. So we call it transforming the problem. Yeah, so this kind of commonly used method in problem solving. After that, we improved our results significantly from 3 multiplication before the transformation to 2 multiplications after the transformation. Yeah. So that's the critical step. Yeah. Here we can say the key to the success, factorization. The factorization technique is the key to the success. Yeah. All right. When we move to the more general case, we want to, apply this technique and push this technique to cover the general case. So that's what we are going to do at this point. Yeah. All right, how to do it? Here. To do that, we need another strategy. So you can see we keep using a lot of strategies. So here, another strategy. We need it. So what kind of strategy? Yeah. Do factorization as much as we can. We know the factorization is the key to the success. In order to make this kind of success even bigger, to cover the general case, we want to do it as much as we can. How do we understand this part, as much as we can? Okay, pretty vague, right? Pretty vague. Yeah, here, there is some interesting terminology for this method, for this idea. So what's that? It's called a greedy idea. Greedy idea. And there is a famous algorithm. It is called a greedy algorithm. Greedy algorithm. Yeah. So for this class, actually, we, based on how much time we could have near the end of semester, if we have some time, I will give you a few more examples using the greedy algorithm. Yeah. But that part is optional. But here, I want to introduce this idea, greedy idea. Yeah. All right, so that's very simple. We can apply some effective method as much as we can. That's greedy. Yeah. Greedy, we try, actually we extend original meaning. Greedy, someone trying to get money as much as he can. Greedy. Yeah. But here we try to get some valuable property as much as we can. Yeah. So this kind of analogy we use here. Yeah. All right, so let's do our work. Yeah. In order to apply the greedy strategy. Yeah, greedy is also a strategy in order to apply this greedy strategy. So let's work it on another special example, because at this point we do not have enough experience. We need to collect a little more experience before we can go to the general case. So let's work on the case for n equals 3 here. N equals 3. Yeah. The polynomial for this case, we call it cubic polynomial. Cubic polynomial. Okay? All right. All right, so you can see here, can we apply the factorization technique as much as we can, right? As much as we can. Yeah. In another description here, so what do you mean as much as we can? So we provide another description. So that's the one you see here. The factorization should cover as many terms as possible. So that's the a little more specific interpretation on that, as much as we can. Yeah. So the specific operation is like this, or transformation is like this. Yeah. We group the last 3 terms. They all have the same common factor x. So let us just factor that out. Yeah. So here you can see, after factorization, inside the parentheses, we have a quadratic polynomial, right? Yeah. After the factorization, inside the parentheses, we have a quadratic polynomial we just considered before. So we're familiar with that. So we can apply another round of factorization on the quadratic polynomial inside the parentheses. Yeah. After that, we change or transform the original polynomial to a new form. In this new form, we did factorization twice. Twice. Yeah. That's as much as we can. Okay? Push to the end. That's the maximum amount of factorization we can do. Yeah. Yeah. Now let's count the number of multiplication we have. The number of multiplication we have here. Yeah. Look at the first one, 1. Second one, 2. The third one, the last one, 3. So you can see at this point we get 3 multiplications. How about that? Is that good? Okay. How much improvement do we have comparing with the old method? For the old method, 1 multiplication here, 2 multiplication next term, 3 multiplication the last term. Adding together, we get 6 multiplication. So we reduce from 6 multiplication to 3 multiplication. We cut the number right in half. 6 becomes 3. That kind of reduction, 50% reduction. Bigger than before. The quadratic case, we did 33% reduction. Now it becomes even bigger, 50% reduction. How about that? Much better? Yeah. So it's very encouraging. So that means this is a, excellent direction. Yeah. We should go this direction. All right. Now, after these 2 examples, I think we get plenty of experience. So now we are ready to go to the general case. All right, now push to the general case. We do the factorization as much as we can in this fashion. How about that? This fashion. Okay, so you can see that is a straightforward generalization from that cubic polynomial. Okay, pretty straightforward. Yeah. All right, so now for this general case, yeah, so I can put a, P sub n here. Yeah, P sub n of x equals this general polynomial. Now my question, can you tell me how many number of multiplications do you have in this new format, new structure you can take advantage of? Can you count it? The technique I just, introduced in the previous, part B. Can you apply that technique another time to give me the answer, the number of multiplications in this polynomial structure? Yeah. All right, so let me show you again. Here, I introduce a famous algorithm. It is called Horner's rule. The title of this video, Horner's rule. Very famous. Okay, now the trick is here. After you see the simple trick, but very effective and very powerful. Okay, all right. Horner's rule, we will, to count the number of multiplications, we use our old technique, counting by reference. Okay, so let's look at how do we count it. Okay, the first multiplication here, can we associate with something, another mathematical object that is easier to count? Okay, we can associate with the subscript here. Okay, A1, the subscript here. All right. Second multiplication, can we associate with the next subscript 2 here? Can we do it? Da, da, da. Okay, yeah. No matter what are they, what are those terms inside that da, da, da. Okay, so this one we can associate with subscript n minus 1, and the last one we associate with subscript n. Now you can see counting the number of multiplications, it is equivalent to counting the number of subscripts, 1, 2, 3, all the way through n. How many? Obvious, n. N multiplications. So simple. Yeah. Hope you can understand this technique, counting by reference, better. Yeah. All right. So now count the number of multiplications. The answer is n. Okay. All right. Now let's get to this multiplication reduction part. How much? The reduction we have. Before the reduction, we have this formula, 1/2 times n plus 1. Yeah. After the reduction, it becomes n. Okay. So we know it is a pretty big improvement, right? Yeah. But the question is, how much is the difference? Do we have some clear idea how much is the difference? Yeah. Here, let us use the next slide to try to visualize the difference. We want to feel about it, how big it is. So let's do some more work to see it. Yeah. All right. All right, so let's look at, we try to get a, better understanding here. The impact of multiplication reduction, how big. We want to visualize it. We want to get a, better visualization here. Yeah. How to visualize the improvement. Very simple. Yeah. Here I just want to use two simple examples. With these two examples, you can get a, much better, impression on the improvement. All right. So let's look at the first example when n equals 1,000. Let's compare the two numbers before reduction, after reduction. Before reduction, 1,000 multiplications. But after reduction, you plug in 1,000 for the variable n in the left-hand side formula. Approximately, this number may not be precise, approximately 500,000. It's a big number. But when you compare these two numbers, when you take the ratio, you get 500 to 1. Is that big? 500 to 1. Is that difference big? Yes, it is big. Okay? Yeah. Next example. We take much larger n number, 1 million. So this time, let's compare these two multiplication numbers before and after reduction. Before 1 million. Okay? Plug in to the left-hand side formula 1 million and we get this big number. 500 billion. How big it is? 500 billion. Okay? Yeah. Ratio again, yeah, because we want to see, comparatively, yeah, how big is the difference. So we take the ratio. This time we get 500,000 to 1. 500,000 to 1. How big it is? 500,000 to 1. How big it is? Can you get some visualization? May not be easy, right? It's a big number, but you may not have a good idea how big is the difference, right? Yeah. Here, let me use a concrete way to impress you. So what's that concrete way? Let me use our real world experience for that. So this time, I take the time unit S, 1 second. Yeah. Here, 500,000 to 1, this 1 corresponds to 1 second. 1 second, okay? That 1 corresponds to just 1 second, all right? Then, the other side, 500,000, that's 500,000 seconds. 500,000 seconds. How long it is? Because here, how do you know? Do you know how long is 500,000 seconds? You may not have a clear idea, right? Let us convert it to time unit days, number of days. Then you have a clear idea. Okay, 500,000 seconds equals how many days? Then you have a better understanding here. Approximately 5.8 days. Very close to 6 days. Think about that, 6 days versus 1 second. Is that difference big? Huge, right? Yeah. All right. Now, with these two numbers, we can have our visualization. So what's that visualization? Yeah. Here it is. You have two algorithms, a bad one and a good one. Okay? When you use the good one, you can solve a problem in 1 second. That's pretty fast, just 1 second. So you type enter, after 1 second, you see the answer. But when you use that better one, okay, when you use that better one, after you hit enter, then you need to wait 5.8 days, approximately 6 days. So you can do your other things. 6 days. You need to wait 6 days. So you can, even travel, to some place. After you come back, about 6 days, then you see the answer. But these two algorithms just work on the same problem. One just 1 second, another 5.8 days. Is that very impressive? That difference? Do you think our new algorithm, Horner's rule, very impressive? Yes. Yeah. I plan to give you first project on this Horner's rule. Try to impress you with this huge difference. All right. So tomorrow I will talk about this project. Yeah. Let me stop this video right here. Yeah.